Hello everyone, this is Abilino Dawis, your instructor. In the previous lecture, we have considered the analytical solution to the swing equation of the rotor angle, wherein we determine that when the roots of the characteristic equation are complex pair, meaning when the synchronizing power is at the left side of the sine curve, where the our synchronizing power is positive, then we obtain complex roots for our uh, characteristic equation, and which we say that the our generator is stable. But when the roots of our characteristic equation are real and distinct, meaning because we obtain two roots for our characteristic equation, and this means that when the synchronizing power is negative, no, meaning at the right side of the sine curve, then we have seen that our generator will be at unstable condition. Now, this time, we will consider the equal area criterion for stability. Now, equal area criterion of stability is a graphical method of determining whether the system is stable or not. This criterion is applicable to any two-machine system for which commonly made assumptions are made. It is also applicable to one machine now swinging with respect to an infinite bus. An infinite bus is one with a constant voltage source. Okay, its internal impedance is zero and its inertia is infinite. Now let us consider the simple network shown below, where we have a generator and then supplying a load now through this transmission line with the reactance XL. We have buses 1 and 2, where bus 1 is for the generator and bus 2 is for the load. Now at normal condition, the generator is supplying power to the load. We can draw the power angle curve then as before. So the power angle curve of our generator is a sine curve, where we have here equal and the electrical power developed in the rotor of our developed in our generator is equal to P max sine delta, where our P max would be equal to the product of the magnitudes of V1 and V2 over XL sine delta. And we have here the operating point of our generator at point A, where we have the mechanical power input equal to PM. So at A, PM is equal to PE, where the generator has a rotor initial rotor angle displacement of delta O. So this would be the equilibrium condition of our generator. Now, point A is the normal operating point of the system, where as we have seen, PM is equal to PE at this point, and delta is equal to delta O. Now, suppose a three-phase fault occurs at bus 1. The generator terminals are short-circuited, so its terminal voltages or V1 becomes 0. Therefore, the electrical power P suddenly drops to 0 since V1 becomes 0. As we have seen on the equation for our electrical power. So if B1 is equal to 0 here, then P is equal to 0. And this is shown by line AB in the power angle curve. So from A, when the terminals of our generator are short-circuited, such that B1 becomes 0, so that electrical power is equal to 0. So the electrical power suddenly drops to from A to point B, while the mechanical power is maintained constant at this particular instant. However, okay, PM remains okay the same. So the accelerating power PA equal to PM minus PE. When PE becomes 0 at point B, so our accelerating power becomes okay large, okay, causing the speed of the generator to increase. So the generator speeds up. Now in turn, this causes the okay, rotor angle of the generator to increase now from delta O to delta C as shown when the fault was cleared by the breaker. So at point C, okay, the fault was removed no, through the action of the circuit breaker. Now when the fault was removed, okay, the electrical power output suddenly increases okay, to point D okay, on the power angle curve. When the fault was removed, the electrical power output suddenly increases to point D on the power angle curve. So from point C, when the fault was cleared, okay, the electrical power suddenly increases okay, to point D no, along the okay, power angle curve. Okay, so at point D, PE exceeds okay, PM. So at this point, okay, since PM remains the same, so the electrical power at point D is greater than the mechanical power PM. So PA equal to PM minus PE becomes negative because okay, this PE is greater than PM. So therefore, PA is okay, negative. Now, as a consequence, okay, the rotor slows down as PE goes from D to E as shown. So, from point D, uh, because PE is greater than PM, so the speed of the rotor of the generator okay, slows down up to point E, which corresponds to okay, delta G. Okay, so at point E, okay, delta is equal to delta Z. Now, at E, okay, the rotor speed is again synchronous. Okay, the angle delta G is determined by the fact that area 1 and area 2 must be equal. So, the rotor angle slows down but still the it follows along this curve until it stops at point E. Okay, now point E is the point okay where okay our area 2 okay would be equal to area 1 no? Area 1 as shown in this diagram okay is the area of this rectangle okay with the PM as the boundary here, and we have 0 down, and then we have this okay height no, or the side of this rectangle, while here we have okay to get the area under the sine curve okay such that okay by area equal area criterion okay A1 must be equal to A2. So whatever is this area, so the corresponding side here okay for A2 should be such that it will stop at point E no, so that A2 will be equal to E1, and this corresponds to our angle okay delta G. Now, the accelerating power at E is still negative, meaning retarding. And so the rotor cannot remain at synchronous speed, no, but must continue to slow down. So the relative velocity is negative and the rotor angle okay, moves back from delta G to E. At E along the power angle curve to point A, at which the rotor speed is less than the synchronous speed. So, okay, from E, okay, because the retarding torque is negative, so it causes the rotor to slow down. So, the electrical power okay decreases okay from E and moving towards okay A, at which okay at this point okay the speed of the rotor is less than the synchronous speed no, the synchronous speed occurs at point E. Now from point A to point F okay PM is greater than okay PE, So from A, because it cannot stop at point A, it has to move down, okay, along the curve, okay, where at this point, okay, PM now is greater than PE. So PE is here and PM is here. So our PM is greater than PE. So the rotor increases its speed, okay, until it reaches synchronism again at point F. So along the curve here, okay, the okay, rotor will attain its synchronous speed at point F, okay, where point F is located, okay, such that, okay, our area 3, you know, from point E, okay, should equal to area 4, no, from A to F. So in other words, okay, if we solve this area here A3, now the area A4 bounded by PM, okay, and this side and along this, okay, sine curve, now should be equal. In the absence of damping, the rotor would continue to oscillate in the sequence, okay, from F, then to A, then to E, and then from E to A and to F. So this will continue, okay, swinging if there is no damping. But if there is damping, then uh, when it goes back to this point, it might not reach anymore to E, no, because of the damping effect. And then it goes down again, passing through A, and it will not reach anymore to F because of the damping effect. Now, when it rises again, okay, it will not reach to the previous point, but somewhere here, no? And then it goes down again, 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 until it goes back to, okay, point A. So it's that, okay, movement. So therefore, the equal area criterion merely states that whatever kinetic energy is added to the rotor following a fault, okay, must be removed after the fault, okay, to restore the rotor to synchronous speed. Now, the shaded area A1, okay, is dependent upon the time taken to clear, okay, the fault. So it depends on this area A1 here. It depends, of course, okay, when we can clear, okay, the fault, now represented by delta C. Now, if there is delay in clearing the fault, the angle delta C, okay, is increased. Okay, so if the clearing is further delayed, no, this okay, our delta increases from delta O to a larger value. Say we call this as delta CR, where we call this as the critical, okay, angle. Now the angle delta C is increased. Likewise, the area A1 increases. So our new A1 here, when delta is increased, okay, will be larger than, okay, the A1 that we have here. And the equal area criterion requires that A2 also must increase, not to restore the rotor to synchronous speed at larger angle of maximum, okay, swing delta G. Okay, so it requires that, okay, when delta 1, no, when area 1 increases, so area 2 also must increase, okay, so that delta G will, okay, move, no, also to a new, okay, value, okay, such that, okay, our A2 would equal to A1. So if the delay in clearing is prolonged so that, okay, the rotor angle swings beyond, okay, the maximum delta, then the rotor speed, okay, at that point on the curve. Now when this is a delta max, the power angle curve is above synchronous speed, okay, when positive accelerating power is again encountered. Okay, so it's this. Now, under the influence of this positive accelerating power, the angle delta will increase without limit and stability occurs. So meaning, when the rotor angle, okay, increases beyond delta max, okay, the accelerating power here is okay greater than PE again, no? Because this is PM and our P is this. So the uh, the accelerating power will increase, causing instability to our generator. So therefore, there is a critical angle delta CR, okay, for clearing the fault in order to satisfy the requirement of the equal area criterion for stability. So this delta CR here, no, this is the critical value of delta such that okay beyond this, okay the delta on the other side okay would be greater than delta max. So this is what we call as the critical clearing angle delta CR. And the corresponding critical time okay for removing the fault is called the critical clearing time, okay, TCR. Okay. Now to calculate delta CR and TCR, okay, we have to find okay the area, the two areas A1 and A2. Now for A1, it's okay. Actually, the integral okay from delta O to delta CR of okay our function here in this case constant it's PM okay times okay the differential element now here which is d delta. So it is just equal to PM okay because PM is constant and we integrate this with okay with respect to delta, so we just have delta and then we substitute okay the limits, so we have delta CR minus delta CO, which is just okay very plain that for the area of a rectangle okay we just determine okay the side, so this okay side here is PM and then this side is PM and then this side is delta CR minus delta O. Okay. Now for the second area A2, now we need to integrate now between from delta CR to delta max. So we integrate delta CR or delta max, and okay the upper curve here is our PE, which is equal to P max okay sine delta okay minus the okay curve bounding at the bottom, so which is just okay PM. Okay, and then now integrate this with respect to delta delta, d delta here. So computing, okay, so we just have equal to P max, okay, then uh, we distribute the delta delta, so integral of sine delta d delta is cosine, okay, delta, and then we just have here PM, okay, delta, no, which is this. So when we substitute the upper limits, so for this, when we have P max, okay, cosine delta, so upper limit is uh, integral of sine is minus cosine, no? So we have here okay cosine of delta CR minus cosine of okay delta max, and then minus okay the this integral here, the PM okay the delta evaluated from delta CR okay to delta max, so we just have PM okay delta max minus delta okay CR. So equating okay these two because we have equal area criterion, so A1 is equal to A2, and solving for delta CR okay we find okay delta CR equal to PM over P max okay times okay delta max minus delta O plus cosine of okay delta max. Now from the power angle curve, our delta max okay would just be equal to pi, which is this, no, or 180 degrees, and then we subtract okay delta O, no, because our curve is okay symmetrical. Okay, so this delta O here with the same point here, the same line, okay, intersecting the curve. Okay, so okay, this angle here must be equal to this angle. So this is equal to delta O. So therefore, if this is okay pi, then our delta max would be okay pi minus this, which is delta O. So we have this one. And Pm is equal to P max, okay, sine delta O from our equation. Okay, for Pe, no, because Pe is equal to Pm is equal to Pe. So therefore, our delta Cr, okay, will just be okay equal to the cosine inverse of okay pi minus 2 delta O, okay, sine delta O minus cosine okay delta O. And to determine okay the critical time TCR, we need to go back to our swing equation where we have okay 2h over omega s delta squared delta dt squared equal to Pm minus Pe. Now Pe is equal to okay 0. So our equation then would be the second derivative of delta okay equal to omega s over 2h okay times Pm. So integrating the second derivative of delta, we just get okay the first derivative, while at the right we integrate from 0 to t of omega s okay Pm times dt, or we just have okay ws 2h okay Pm times t. Now we integrate further, so the integral of this is equal to delta, while integrating this with respect to t, we get okay ws or omega s over okay 4h okay Pm okay t squared, no, because we integrate this with respect to t, so it becomes okay t squared, and then now we have the constant of integration, okay, which is just our initial angle okay delta O. So when delta is equal to the critical angle delta CR and T is equal to the critical time TCR, so our delta CR would just be equal to okay double omega S times Pm over 2h times the square of the critical time okay plus delta O. So solving for TCR, okay, it will just be equal to okay 4h times okay delta CR, and then we transfer this to the left, so minus delta O, and then denominator we have okay omega s okay over Pm. Now let's have an example. Okay, calculate the critical clearing angle and the critical clearing time when the system is subjected to a three-phase fault at generator bus. At normal condition, okay, the electrical power developed and the generator is given by PE equal to 2.10 sine delta okay, per unit, and the initial rotor angle is delta O equal to 28.44 degrees, or this is equal to 0.496 electrical okay, radians. And the mechanical power input PM is 1.0 per unit, and H is equal to 5 megajoules per MVA, and omega S is 377 radians per second. So for our solution, our delta CR would then be equal to cosine inverse pi minus okay, 2 delta O sine delta O minus cosine delta O. So substituting the values okay, for delta O, so we have okay this one, and we just get the inverse of this. So our critical rotor angle delta CR is 81.69 okay 7 okay degrees, or this is equal to 1.4 okay 26 okay electrical radians. So our delta CR here is near okay 90 degrees already, no? For the generator to remain okay stable okay when the fault is not okay removed okay at shorter time. And the critical time, therefore, from our formula, which is equal to square root of 4h times delta CR minus delta O over omega S, okay, times Pm, So substituting the values, we get, okay, the critical time to be equal to 0.222 okay, second.